Have you ever stopped to think about the invisible forces that make our modern world, well, work? There's the secret principle, this kind of magic frequency that's behind everything from tapping your credit card to heating up your soup. So, let's pull back the curtain and dive into the incredible power of resonance.
I mean, seriously, just think about it for a second. Every time you tap to pay, you're part of this tiny, high-tech miracle. A simple piece of plastic talks to a machine, sends your info, and finishes the deal, all in the blink of an eye.
And here's the real head-scratcher. There's no power source in that card, right? No little battery, no plug. So where does it get the juice to even send a signal? To figure this out, we need to zoom in and listen to a conversation happening between electrons.
The whole secret is right here, in this interaction. The payment machine sends out a magnetic field, and a tiny coil antenna inside your card is designed to listen. But for that conversation to actually work, the card's circuit has to be tuned perfectly. And to get what that means, we gotta meet the components that make it all happen.
All right, so to really understand this tuning, we need to get to know the three main players inside a basic alternating current, or AC, circuit. These guys are the building blocks of all the magic we're talking about. First up, we have the resistor. Think of it as the simple, steady gatekeeper of the group. Its job is really straightforward. It just resists the flow of current. It doesn't care if the frequency is high or low. It provides the same opposition no matter what.
And you can see its personality right here in this graph. See how the waves for voltage and current are perfectly locked together? They're what we call in phase. The resistor is predictable, reliable. But trust me, things are about to get a whole lot more interesting.
Next, meet the inductor. At its heart, it's just a coil of wire, but it has a very strong opinion. It hates change. It builds up a magnetic field to fight back against any shift in the current flowing through it.
Now, because AC current is always changing direction, the inductor is constantly putting up a fight. And the faster the current tries to change, meaning the higher the frequency, the harder the inductor pushes back. You can see it in the graph. All that resistance makes the current fall behind or lag the voltage.
And our last component is the capacitor, which I like to call the energy reservoir. It stores up energy in an electric field. Now, it will completely block a steady, direct current, but because it's always charging and discharging, it lets that constantly changing AC current flow through.
And here is where it gets really cool. A capacitor is the polar opposite of an inductor. Because it charges and discharges so fast, it actually passes high-frequency currents way more easily than low-frequency ones. This makes the current get out ahead of, or lead, the voltage. So you've got the inductor, which hates high frequencies, and the capacitor, which absolutely loves them.
So, what do you think happens when you put these two total opposites in the same circuit? Well, you get this amazing conflict, this electronic tug-of-war, with frequency as the rope.
Let's look at the matchup, side by side. The inductor's opposition, we call that reactance. It goes up as the frequency goes up, and it makes the current lag behind. The capacitor's reactance does the exact opposite. It goes down as frequency goes up, and it pulls the current forward. They are in a constant battle, pushing and pulling.
Okay, so how do we keep score in this battle? We use a value called impedance, which we write down as the letter Z. You can think of impedance as the grand total of all the opposition in the circuit. It's the resistor's steady pushback plus the epic, frequency-dependent struggle between the inductor and the capacitor.
And this brings us to the most important part of the story. You see, this tug-of-war has a very, very special outcome. There's a sweet spot, a point where the whole battle finds this perfect and incredibly powerful balance. So, let's ask the big question. What if we could tune the frequency to that one perfect value? The exact spot where the inductor's backward push is perfectly matched by the capacitor's forward pull. What happens then?
At that one magic frequency, their opposing forces completely neutralize each other. It's not a fight anymore, it's a perfect handshake. As far as opposition goes, it's like they just vanish.
And that right there is resonance. It is the circuit's own natural favorite frequency. It's the one perfect spot where it's tuned to let energy flow through with almost zero resistance.
The result? It's absolutely dramatic. When you hit resonance, the total opposition, that impedance we talked about, it just collapses. The only thing left putting up any fight is our boring old resistor. With the inductor and capacitor effectively out of the picture, the current just surges through the circuit, hitting its absolute maximum.
And check this out. This is what it looks like in the real world. As you dial in the frequency, the lamp gets brighter and brighter until, bam!
it hits its peak. That brightest point is the resonant frequency. It's the physical proof of that massive current surge when the circuit is perfectly in tune.
So, now that we know about this powerful idea, let's go back and finally solve the mystery of that powerless little payment card.
See, that payment terminal isn't just blasting out a random magnetic field. It's broadcasting energy at a very, very specific frequency, 13.56 megahertz. And the circuit inside your card, it's been meticulously engineered with just the right inductor and capacitor so that its resonant frequency is, you guessed it, exactly 13.56 megahertz. The moment the card gets close, the circuit resonates, its impedance drops to almost nothing, and a rush of current flows, just enough to wake up the chip and send your payment info. It's not magic at all. It's just beautiful physics.
And once you get this, really get it, you start seeing it absolutely everywhere. This isn't just some neat trick for credit cards. Resonance is one of the most fundamental principles driving our technology.
You know that induction stove in your kitchen? It's using a resonant circuit to create a super powerful magnetic field that heats the metal in your pan directly. Or how about the traffic sensors under the road? Those are just big inductive loops tuned to a resonant frequency. When your car, which is a giant chunk of metal, drives over it, it messes with the field, detunes the circuit, and boom, the traffic light knows you're there.
From tuning into your favorite radio station to the incredibly complex physics of an MRI machine, resonance is the secret that makes it all possible. So the next time you tap your card or make dinner, just think about that invisible dance of energy happening all around you. And maybe ask yourself, what else in my world is secretly tuned in, just waiting for the right signal to spring to life?